it turns out that there's a nice relationship between the greatest common divisor and the least common multiple, which is not terribly well known. But let's explore it. So let's let a and b be positive integers. In fact, I want to let a and b be positive integers. Say a and b are greater than or equal to 2. Actually, I need a little bit more than positive. I want them to be at least 2. The reason for that is that I want to be able to talk about the prime decomposition of a and b. So I want to be able to think about a and b as being written as a product of primes. And what I want to do is I want to explain the following. So let's look at two numbers. So I'll state this and prove this in a second, but let's first give an example. So let's look at two numbers. Let's say we're to pick a, which is 2 squared times 3 times 7. So that would be 12 times 7 or 84. And b, let's say, is 2 times 3 times, let's do 2 times 3 cubed times 5. So that would be 1250. Okay, nope, just kidding. That would be 270. Okay, so 270, because 3 cubed is 27, times 2 times 5 is 10, so 27 times 10, yeah, there we go, 270. Now, if I wanted to compute the greatest common divisor of 84 and 270, what we would do is we would look through the prime decomposition, and actually this is more than just a prime decomposition. I'm going to take all the primes that are a factor of at least one of these numbers. And so this is not exactly a prime decomposition because I'm going to include numbers that aren't actually divisible by here. So I'm going to put a 5 to the 0. 5 is not a factor of A. And likewise, I'm going to put a 7 to the 0. 7 is not a factor of B. But having the same set of prime divisors is helpful. So it turns out that one way to think about the greatest common divisor is to go through and to look at each of these sets of primes, 2, 3, 5, and 7 in this case. And to find the GCD, what we're going to do is we're going to take, we have 2, 3, 5, and 7, and we're going to use the exponents that are the minimum exponents in either A or B. So for A, we have 2 squared and 2. So the smallest there is 2. This is 2 to the first. And then we're going to have 3 and 3 cubed. The smallest there is 3. And we're going to have 5 to the 0 and 5 to the 1. The smallest there is 5 to the 0. And 7 to the 0 and 7 to the 1. So 7 to the 0. So the GCD is going to be 6. So what you do is you pick the minimum exponent. On the other hand, the least common multiple, to find the least common multiple, you pick the maximum exponent. And so what you do is you would look at 2 squared and 2, and you would pick 2 squared. And 3 cubed and 3, and you would pick 3 cubed. 5 to the 0, 5 to the 1, the largest is 5. And 7 to the 0, 7 to the 1, the largest there is 7. So whatever that product turns out to be, I'm not going to compute it, but whatever that product is, that'll be the least common multiple of 84 and 270. Now, what's really going on here, and let me say this, the proposition is that if you were to take A times B, if A and B are integers greater than or equal to 2, that's going to be equal to the GCD of A and B times the least common multiple. So this is true of all positive integers. Again, integers greater than or equal to. Really, this is true of all positive integers. It's just meaningful when A and B are not 1, of course. So this is true. And the way that we prove this is that it turns out that to find the GCD, we use the minimum exponent. To find the least common multiple, we use the maximum exponent. And it turns out that this follows from, so this is kind of a proof sketch, but this follows from the fact that if you were to take the maximum of two numbers and you were to add to it the minimum of those two numbers, you would always end up with x plus y. So not a very deep fact, but this is essentially what the proof relies on. The details are in the lecture notes. Okay. In particular, so as a corollary, it turns out that two integers a and b are relatively prime So two integers a and b are relatively prime if and only if, so if and only if, the least common multiple of a and b is the product a times b. And I'll let you think about the proof there and why that should work.